Welcome back to ECE 220. Announcements. This has been fairly common this week. Today's office hours will be held immediately following class instead of at 11 today. Just today. I think for the rest of the semester we'll try for the normal 11 to noon time. You have an assignment. I'm not really checking on that assignment whether you complete it or not, but that is to watch the tutorial on PSpice, and that's designed to help you complete what's listed at the bottom, which is your PSpice homework. And if you follow along on that tutorial, that essentially completes the first half, I think, of your PSpice homework. So that homework shouldn't be too difficult, but you will want to make sure and get it done by a week from today. And I want you to turn that in class, a hard copy with your name on it. And if it consists of 2 pages, make sure those are combined in some way with a small staple if possible. The orientation labs, lab number 0s, begin next week for Group A. And make sure that you bring something to those labs to take notes with. Homework 2 is due on Tuesday of next week, and I went ahead and included the additional homeworks that will be due prior to exam number 1, but exam number 1 will only pertain to material on homeworks 1, 2, and 3. And if you want information on exam number 1, I would recommend that you look at the practice exams that are available to you through the link on D2L. We're finally getting there. We're finally going to divide current. We've been dividing voltage a lot. Today we will start with, instead of continuing to put it down on the list, let's begin with the current divider and work through that. Some examples with a somewhat common 2-branch circuit, then a more complicated 5-resistor network, and then we'll get into bridge circuits. Notice there's a circuits after the bridge, where this is not a civil engineering class where we're talking about bridge design. Now we're talking about bridge design in ECE, and what does that mean? And when is our bridge balanced? That we will try to get through today. And that really, once we have a bridge network of resistors, we can't do the simple series parallel combinations. We now have to resort to Y delta or delta-Y transformations. Can we transform a delta configuration of resistors into a Y or vice versa? That usually will help us in the analysis of these circuits that involve bridge networks of resistors. And you may see, and in the text they talk about a particular bridge, a Wheatstone bridge, and where inside or that bridge resistor, now that's actually replaced with a measurement device, and that you could measure current or voltage. Typically it's measuring current, and you're trying to adjust resistors in this Wheatstone bridge configuration to accurately measure one of the 4 resistors circling that particular bridge measuring device. That will hopefully start to become clear when we start going through these examples where we have a unbalanced bridge circuit, which means that there is voltage dropped across that bridge resistor, and when we have a balanced bridge circuit where there is no voltage drop, or we could equivalently say there's no current flowing across that bridge resistor. And that simplifies the analysis, but we will talk about these conditions for when a bridge circuit is balanced as we go through these examples. As I said, let's start now with this current divider circuit. We talked about voltage division when we had two resistors. Let's start with a two resistor case on current division. And here, with the same thought process, now we want to know how is that source current, I sub s, divided among those two different resistors, R sub 1 and R sub 2. You would expect, if R1 and R2 are not the same, that you will have different current flowing in the two different branches. But here you just have the single independent current source, so there's no other current that could sort of arise magically in that circuit. That source, the value of that current has to be split somehow between R1 and R2, and our objective now is to determine what I1 looks like, maybe in terms of R1, R2, and I sub s, and what does I sub 2, a formula for I sub 2, look like. You can already analyze a lot of this circuit. What is the voltage V? Or how is V related to those different elements in our circuit? Or how are those circuit elements interconnected? They're all in parallel, aren't they? They all experience the same voltage drop, and if that's the case, that voltage V, using Ohm's law, is R sub 1, I sub 1. It's also R sub 2, I sub 2. Or, if you combine those two resistors into an equivalent resistor, the current source sees, when it's looking how much current, or what is the voltage, well, that current source is going to see an equivalent resistance across its terminals, and we could then find the voltage dropped across that current source by multiplying the current source's value, I sub s, times that equivalent resistance. Now, here's your quiz for this morning to wake us up. What's the expression for two resistors in parallel when we want their equivalent resistance? Do you remember what that is? And this you probably want to commit to memory for the duration of the semester. It was a ratio, was it not? Question? I sub s, that's an s. So that I'm using a script s. Somebody said, are you referring to I sub p? Are you insulting my cursive writing? That's fine. My second grade teacher would probably dock me as well, but that's supposed to be a script s. The reason I use script s's is because my non-cursive s might look like a 5, and you go, is that I sub 5? Is that I sub s? Well, here I'm trying to say, so somebody might say, well, is that I sub rho? No, just bear with me. That's my I sub s. So that's the source. That s is standing for source. That's I sub s. I apologize, that piece, the tail, looks like it's going a little too vertical. Maybe it needs to be a little bit more like that. But that's what I was trying to draw, but I just drew it very quickly. That's my S, my cursive S, for the subscript on the source current I. Are we clear on that? If you have questions like that that are really bothering you, let me know, and we'll try to work through those. But that's I sub s. That's what I'm meaning by I sub s. That's the same as if you see it as I sub p. What is the expression? Now that we've figured out who's floating around, that current that's floating around, how do we find the equivalent resistance? What's the expression for that? It's a product and a sum. Which one goes where? Product goes on top, doesn't it? So now we have R1 times R sub 2 divided by the sum of R1 plus R sub 2. That's the equivalent resistance. And now if we just look at these different relationships that are equivalent, we can now find an expression for I sub 1 and I sub 2. Meaning R1 and I1, we just said, is the same as R1 R2 over R1 plus R2 times I sub S. And if that's the case, well, we can cancel a common R sub 1, and now we have our formula for the current in that R1 branch. I sub 1 is now divided, or the fraction of I sub S that makes up I sub 1 is the opposite resistor up top over the sum, R1 plus R sub 2. And now, hopefully, by looking at how we canceled the R1, you understand why that R2 appears up top. Or you could, well, let's derive the expression for I sub 2. It's the same drill. R sub 2, I sub 2 was exactly the same voltage. V, which is this equivalent resistor, times I sub S. In this case, we can cancel the R sub 2. And now I sub 2 is R1 over R1 plus R sub 2 I sub S. We have the sum in the denominator, and then what do we put upstairs? Well, we put the opposite resistor, and now if, for example, R sub 2 was much bigger than R sub 1, and these are resistors, they're resisting current flow, which current do you think would be larger if R sub 2 is bigger than R sub 1? Just intuitively. Which current would be bigger, I1 or I2, if R sub 2 is bigger than R sub 1? You would think I1 would be bigger. And in our formula now, if we compare I1 and I2, do you see that if R2 is bigger than R1, I1 is going to be bigger than I2? Kind of making sure that the formulas are consistent with our intuition. Question? So what's the significance of R2 and R1 paired up with I1 and I2? Is that the question? So I was trying to justify why this formula makes sense, but the left-hand side is the proof. We know V is the same across all of those elements. They're all in parallel. V we can express as R1I1 or R2I2, but we can also express it as R equivalent times I sub S. Making all of those relationships, or setting particular pieces of those relationships equal to each other, we derived those formulas. And I1 now is bigger than I sub 2 if R sub 2 impedes more than R sub 1. Let's look at an example. And here in our example, let me go ahead and say that this resistor is now 2 ohms. And our task is to find both I and I sub 0. From what we've learned so far, what would we find first? I sub 0 or I? Based on what we've talked about so far this semester, how would we approach this problem? I'm trying to sort of put you in your seat in 2 weeks, or 3 weeks, 3 weeks, isn't it? Less. Almost, well, a little more than 2 weeks for the next Thursday, our exam on Thursday. How would you approach this problem if you now were asked to find both I and I sub 0? Would you immediately write down an answer for I sub 0? Probably not. You would probably want to collapse all of those resistors into an equivalent resistor and find I, and then back out I sub 0 from what we just learned, which is the current divider. We know that that I is going to be split between those two branches, and how it is split will depend on the current divider. What is the equivalent resistance presented to that voltage source? Do you see immediately that you could combine those two in series? And then those two resistors in series are actually in parallel with the 3 ohm vertical resistor, and that combination is in series with the 8. Or our equivalent is now 8 plus 3 in parallel with 4 plus 2. Does that shorthand notation make sense? And what is 4 plus 2? Boy, we're really going hardcore on the math skills this morning. We're adding 2 and 4, but we're going to get 6. Now we need to combine 3 and 6 in parallel. And that ends up being 18 divided by 9, or 2. So now we're left with our equivalent (10 ohms). That 50 millivolt voltage source is now seeing across its terminals this R equivalent of 10 ohms. And if you want, you might just say, well, let me just keep track of this. Here's my 50 millivolts. I've now boiled it down to that picture. This is now our R equivalent. And if you wanted, you could now write a KVL or Ohm's law, however you want to do this. KVL says minus 50 millivolts plus 10I is equal to 0. Pardon? Can we use uppercase and lowercase I interchangeably? We just have to be consistent. Here, didn't I start with an uppercase? So I'm going to stick with uppercase. Anytime you see an I, a lot of times somebody might think that's the square root of 1, or I'm sorry, the square root of minus 1. In ECE, I usually represents current, so we're going to let J be our square root of minus 1 in this class. When we want the square root of minus 1, that's going to be J. I typically is a current, whether that's uppercase or lowercase, depends on who's writing the problem, but just be consistent. Don't hit the shift key if you haven't used it already. Here I did use the shift key. I'm using capital I believe, in this example. Or, now if I solve for I end up with 50 millivolts divided by 10 ohms, or I now have 5 milliamps for the current coming out of that independent voltage source. And I can now put that into the picture that I need. Now I'm really sort of pulling back out the resistors that I collapsed earlier. And what I want to now do is have that I injected into the parallel combination of 3 and 6 to find what I sub 0 is going to be. Or I'm just redrawing that to say I now have this picture. Here's I, which is I've now found is 5 milliamps. And it doesn't matter that this 6 was made up of 2 resistors, 2 and 4. I just need to know that it's a 6 total, and that's my I sub 0. And now I want to apply my current divider formula. Is that right? Just making sure everybody's awake on a Friday. I sub 0 needs to be 3 divided by the sum of 3 and 6. 3 is the resistor that's not associated with the I naught. Or now I have 1/3 for I. Or I'm sorry, 1/3 of I for I naught, so that I naught is not quite 2 milliamps. It's 1 2/3 or 5/3 milliamps. If somebody said, well, okay, you found I sub 0, but what's this current? And that's I sub 3 just because it's going through the 3 ohm resistor. What's I sub 3? Do you have enough information? And you could solve this many different ways. You could do a current divider again, or you could say, well, we learned KCL. Can't I apply KCL at that node? You have 5 coming in, and you have I sub 3 and I sub 0 going out. Or now you have I minus I sub 0 making up I sub 3. Another way of solving for I sub 3. Or I sub 3 better be what's left when you take 5/3 away from 5. And does that make sense with our thinking before? I sub 0 is 5/3, not quite 2, and I sub 3 is a little bit more than 3. Does that make sense with a 3 and a 6 resistor in parallel? When they're both seeing or coming into that parallel combination is 5. You would expect more current is flowing in the lower impedance or lower resistance branch, and that's what's happening. I sub 3 is bigger. It's now more than 3, and I sub 0 is less. It's a little bit less than 2. And their sum makes 5 milliamps. Questions on that? All right, then let's go to a different circuit, and let me put together the right labels on these. And the task at hand is to find I sub 0, and this one's lowercase. Go figure. I'm trying to get you comfortable with uppercase and lowercase. Don't go and tell your parents that. Oh, today in our sophomore level class in ECE, we learned how to hit the shift key. I'm paying for what? We want to find I sub 0 in this circuit. How are we approaching this, or what is our thinking process behind this problem? If you're now trying to find I sub 0, can you write an equation and immediately solve for I sub 0? How are we thinking of approaching this problem? It's kind of a pretty circuit, isn't it? I mean, if I could draw, but the shape, the geometric shape, is kind of interesting. I guess that depends on your definition of interesting. How are we going to find I sub 0? And the way it's drawn may be confusing. Now what you may want to do is put on your augmented reality glasses and bend those wires around a little bit. What is happening with the 40 ohm resistor and the 10 ohm resistor? They're actually in parallel, although I didn't draw them that way, did I? I drew one at an angle, but now you want to be able to visualize, wait, they share the two nodes in common. 10 and 40 are in parallel. And if that doesn't seem clear, just redraw it. That's fine. Use the paper that you need to make that clear to you. But the thinking is, what if I could find that current, I? Don't ask me now why I did a capital I and a lowercase I sub, I don't know. But here is capital I. If I knew capital I, could I find I sub 0? That would just be a current divider. Maybe I would be finding it in the other direction, but that would be the negative of I sub 0. How do I find I? So here's the thought process. Here's the thinking. Find I, capital I, and then solve for I sub 0. From what we just learned, which is the current divider. Meaning, if I wanted to know what this voltage drop was, that I sub 0 going against what I want to see, maybe let me just make my own, and I'm going to call that I sub 4. 4 for 40. I sub 4, now I feel more comfortable saying I comes in, capital I comes in, I sub 4 is going to divide out of that. And what's my formula for I sub 4? Well, I know that 40 times I sub 4, that's the voltage drop here, V, and that's the same as 40 times 10 over 40 plus 10. That's the equivalent of the 10 and the 40 resistors times the current into that equivalent parallel combination. Or I've now really just re-derived the current divider rule. And if I know I sub 4, I could then find I sub 0. They're just going in opposite directions. One is the negative of the other one. We'd be done if we had I. So we need I. How can we find I? And this particular circuit is illustrating a point that I now want to make sure that we understand. I have an independent voltage source, 75, and what about that 30 ohm resistor? How is that connected to the independent voltage supply? It also is in parallel with that independent voltage supply. And what's an independent voltage supply say? So it's sharing terminals with a resistor that's in parallel with it. What's going to happen? So here's the observation. We have this voltage supply, what was it, 75 millivolts. And we have this 30 ohm resistor across it. What do we know about an independent voltage source? It's going to supply whatever current is needed and maintain 75 millivolts across its terminals. So that 30 ohm resistor, it's going to receive whatever current it needs, but coming out of those two terminals, it's independent of what that 30 ohm resistor is. We could just forget it. We could move it on the other side in a sense and say those two terminals right here are always going to be at 75 millivolts. Our observation is the circuit is unaffected by the 30 ohm resistor in parallel with the independent voltage source. And so now we could really just say, well, we now have this scenario. Or is it okay if I just put it on the other side if that sort of messes up our thinking? They're in parallel, whether they're on the left or the right, it doesn't matter. Here's plus 75 millivolts. Here's the 30. And now here are the terminals. And what are attached to those terminals? We had a 4 and a 3 in series. We can combine those easy enough to get 7. And then we have 40 and 10. In parallel. And here was the current I that we were trying to solve for. And whatever this is, I sub 3, you could solve that immediately using Ohm's law. What is I sub 3? Through the 30 ohm resistor. V is equal to IR, or V is equal to RI. So I is V over R. This is now 75 millivolts divided by 30. And that's now 2.5 milliamps. And that's going to be flowing no matter what's hanging off or connected to the right side. You want me to go back up where? This was I sub naught. Is that true? Is that what we were trying to find ultimately? How do we find it? Now do you see that we could collapse those two to quickly find capital I? Now we have an 8 ohm in series with the 7 ohm connected to this 75 millivolt source. Was that 75 millivolts or volts? Oh, you guys, wake me up. What are you doing? The question was, how much do we simplify? And going into exam 1, yes, we simplify the circuit as much as we can in order to analyze or solve for different variables. In chapter 4, we're going to just start learning additional strategies that involve multiple equations and multiple unknowns, and then we'll get comfortable doing the linear algebra for that. I have volts for amps. What's wrong with that? Thank you. So 2.5 amps. Where else have I fallen asleep? Are we okay now? Pardon? You're all falling asleep, really? I'm that boring? All right. Well spoken. Now, what do we have? We have this and that. This is 75 volts. So let's go a little bit quicker. Here's now I. I is now 75 divided by 15, or 5 amps. If that's I, we now know how to divide I and obtain this I sub 4. We use our current divider in that rightmost piece of our circuit. I sub 4 is 10 over 10 plus 40 times the I that we just found, which was 5. This is now 10 over 50, or 1/5 of 5. This is now 1 amp. Or I sub 0 was just the negative of I sub 4. I sub 0 is now minus 1 amp in our original circuit. Pardon? So I sub 0 meaning minus 1, that means however we sketched I sub 0, we have a negative current in that direction, which really means I sub 4 is a positive current going from, or a positive current going down and to the left. Let's now talk about bridge circuits and Delta-Wye transformations. We're building these bridges out of either stacking, in a sense, two deltas on top of each other, a top and a bottom, or you might, do you see if you, instead of that node being a point in the middle diagram, if you simply expanded that node out and made the far right diagram, do you see now you have this pi circuit? So you might hear this called a delta, you might hear it called a pi. But I hope you can see that they are related. Here is a Y or a T configuration. Now the Y could be upside down, it could be right side up, or it could be flattened out in terms of the Y's could now come down and become horizontal, the arms in the Y, to become a T. What we're really wanting to do is, if we have one or the other in our circuit, it may help us. A lot of times we're going to have a delta. We want to replace it with an equivalent Y interconnection so that we can perform our series parallel combinations. When we have a triangle, then or a delta, it's not easy to analyze the circuit. Here's our bridge circuit. And getting colorful, but those colors will start to, I hope, make sense in a minute. The bridge is R sub 5. That's bridging across the two nodes, the node on the left, and I may call this, just to try to keep track of the ordering or the structure of these R's in this circuit. I have odd subscripted R's on the left. I have even subscripted R's on the right. I have R1 and R3 on the left. I have R2 and R4 on the right. And the bridge connecting them contains a resistor R sub 5. What I want you to be able to see is how you can actually stretch to get from left to right. Do you see all I'm doing is I'm simply expanding the top pointed node into a line and the bottom pointed node or dot, single location, into a line to separate the bottoms of R3 and R4 and to separate the tops of R1 and R2. These you should be comfortable seeing either way or writing them down. They are equivalent interconnected resistor structures. Are we comfortable with going from left to right? That's the exact same network. Now what we want to do is get comfortable going from, bear with me, I'm going to try to do something here that's pretty dangerous. But now I just shrunk the paper. Try that at home. But now I'm trying to go from the top to the bottom. And I've tried to color it so that you can see what has happened. Think of that N1 node, or the yellow highlighted node, being stretched and pulled over and now going vertical. That now places R2 in a horizontal position, and R1 is also horizontal. I've now gone counterclockwise with that magenta highlighted node and expanded it in such a way that R sub 5 now is also vertical. But I am still maintaining the exact same interconnections of R1 through R5. I haven't changed how those resistors are interconnected. And finally, the blue highlight really just stays put. It's just now R4. I'm making that node that it experiences in the top, well, the wire connecting R4 and R5 and R2, I'm going a little bit longer on the R4 wire and bending it so that it now allows R4 to be isolated on the right. Pardon? So the last one might be a little confusing, but you want to get comfortable with seeing it in that way, because somebody might interconnect a circuit like that and you go, well, that's just this bridge network. And then maybe the bridge looks a little bit more intuitive to you. but you may initially have a problem that is provided to you that looks like that lower diagram. And now you can warp that around to be equivalent to what's up above. And I could put a voltage source or a current source between N1 and N2 in either diagram, and you now know how that's going to be interconnected to the circuit that you want. What we now want to do close enough, is be able to convert. Do you see in this bridge network R1, R2, and R5? You can see a delta, or in the bottom you have a delta with R5 on top and R3 and R4 below. That's really sort of two different deltas. You could take the top delta or the bottom delta. What we want to be able to do is convert those deltas, this interconnection, into a Y. So here what I've done is I've taken the bottom delta and converted it. I want the resistance seen between A, B, and C to be the same in this delta configuration as it is in this Y configuration, and we need to figure out what those question marks are. But if I can now replace the delta with a Y, this is now going from delta to Y. Do you see how that's maybe simplified my analysis? I now have R1 in series with this resistor underneath A. I also have R sub 2 in series with the resistor underneath B, and those are now in parallel. And finally, they're in series with that resistor above C. And I can combine those now to collapse all of that mess into an equivalent resistor. And I couldn't before when it was in the bridge configuration. This is trying to motivate the need to go from delta to Y, or we might want to know how to go from Y to delta. Let's now talk about converting from delta to Y and how we might do that. Now we're going to convert in this first example from a delta to a Y. And the idea is the impedance presented, or the resistance that appears between nodes A and B, should be the same in both configurations, the delta or the Y. Likewise, the resistance between A and C needs to look the same, and the resistance between B and C needs to be the same. The way to do it, to go from delta to Y, here's sort of the process. You can sort of visualize this Y inside the delta, and right here is the R1. Here's R2, and here's R3. That's the visual, or the image you kind of want to be keeping track of. To calculate R1, we simply sum the three resistors in the delta and put those in the denominator. 15 plus 12 plus 31K. And now do you see that R1 is touching 15 and 12 on either side? That product goes in the top, in the numerator. And that will provide us with the value for R sub 1. And I didn't calculate that. Maybe if somebody has their calculator, they can tell us what that is. It may not be a clean number. If that's now the strategy for finding these resistors, do you see how R sub 2 came about? In the denominator is simply the sum of the three resistors in the delta, and the numerator is the product of the two resistors that R2 would touch relative to node B, which is 15 and 31. What about R sub 3? Can we write down that expression? Let me make it in blue. What's downstairs? That's just the sum. And what's upstairs? A product. And what's in the product? It's what R3 is touching from node C, which is 31 and 12. And now we've converted a delta into an equivalent Y configuration. I may provide you with a video on why these formulas exist, but this is sort of how you would create those expressions on the fly without the formulas in front of you. We'll pick up at that point on Monday.